Yes? Hello, everybody. Welcome to the Rise of the Evil Robots. Uh, if you can move to the left, you will see better the slides. Up to you. Thank you for joining me today. My name is Dan Horowitz. I'm a product security expert working for Intel. My main focus is on defensive security. So you'll hear today a lot about offensive security. I'm a protector. I have more than 20 years of experience in product security as well as on security products. Worked for different companies in the past, like Checkpoint, McAfee. I even founded some security startups. In my soul, I'm a maker, I'm a hacker, I'm an innovator, and I'm a geek. But most importantly, I like whiskey, better to be smoked, a big beer, coffee short, and cars electric. I'm not an autonomous system expert yet, and not a safety expert. I do have background in autonomous robotics from early 2000 until today. I work on different products, from POC to prototypes, and today I'm part of product development that is focusing on autonomous mobile robots. My opinions today are mine and not my employer, and due to time, I'm gonna do a very, very short overview of industrial revolutions, why we're here, from where we start and where we go. I'm gonna talk a little bit about the autonomous systems, the race of the robots, how safety and security can basically work better together. They are basically the last guardians to prevent those evil autonomous systems to break the laws of robotics. And I'm going to showcase how they can be attacked and how security and safety can prevent those attacks. Those systems basically are sophisticated and complex and can damage human beings as well. Feel free to ask questions at the end, and let me start with some history. So, hundreds of years ago, humans start to utilize animal muscle, invented verbal communication. This is basically the first revolution, the base. Then the real industrial revolution 1.0 focused on mechanization, utilizing of water power, steam power, writing. Our parents witnessed the industry 2.0, the mass production, the assembly line, the electricity. We, in our generation, are witnessing two and a half evolutions. The industry 3.0, it's focusing on computers, electronics and automatization, digitization. The 4.0, it's the cloud, the cyber, the IoT, everything connected, the big data revolution. And we are moving forward in big steps to industry 5.0. I would say we're already in the middle, somewhere around 4.5. So what is Industry 5.0? Industry basically 5.0 will be focused on cognitive computing, AI, autonomous systems, robotization, robots with human-like capabilities, cooperation between human and robots, bioeconomy, beyond meat, and of course quantum computing. And in this evolution, the autonomous systems have a big role, and they are important. But let's talk about a little bit what is an autonomous system. So everyone can imagine robots, self-driving cars, artificial intelligence, everything is around autonomous system. Eventually, an autonomous system, it's the hardware and firmware and software that compose the system that are working together to perform a predefined action. So for a system to be considered truly autonomous, the system must be able to gather information, find a solution based on this information, and execute a predefined action to achieve a specific goal. Autonomous systems basically exist with us as early as 1478. Da Vinci invented the self-propelled cart. In 1866, we have the self-propelled torpedo. in 1947, we seen the first flight, autonomous flight that crossed the Atlantic. In Paris, Metro de l'Ité, France, the first driverless metro. And of course, the first self-driving car was invented by Google in 2012, not so long ago. And if we're talking about robotics, so the early robots were, let's say, invented by Tesla. It is basically a remote control boat. And from there, we start to see as early as 1966 new robots. I want to specify the robot Hilaire, Hilaire 1, invented in French in 1977. Basically, it was the first robot capable of moving autonomous in an unknown environment. And from there, basically, we conquered the skies. We can see those robots exploring the stars like the moon and Mars, so we have the Spirit and Opportunity rover. And today, we can find those robots side by side in different use cases. We have self-driving cars, we have autonomous robots, we have explosive disposal robots, so we already seeing those everywhere down on Earth. They did evolve over this period of time, and the evolution of autonomous system is basically due four specific technologies. So we have improvement in sensor technology, we have artificial intelligence and machine learning, we have better connectivity and communication, and definitely we have enhanced safety. Without all those pillars, today autonomous systems can actually cooperate and behave and exist side by side with us. If you're looking on a specific autonomous system, we can see that it is very rich. It has a lot of systems, subsystems, from vision and sensing and communication and cyber and entertainment and you name it. And they are so complex that they are so easy breakable. The more complex a system is, the easiest is to break it. And I'm not just talking about autonomous cars. I'm talking about autonomous planes, spaceships, submarines, drones. We have them everywhere, from delivery, surveillance, agriculture, and even military. And of course, we also have humanoids. So some examples, sorry, without sound. I have here on the first, it's the Boston Dynamics humanoid, and the second, it's Mentibot. They are both targeted to be released and sell to the market this year. Mentibot is an Israeli company from Mobileye. Look on those nice, cute robots. They're gonna be side by side soon. And they are fully autonomous and capable of many, many interesting things. Just remember, this is like a movie, but it is real. So that brings us to AMRs. I'm going to talk about autonomous mobile robots as a use case, but all the other usages of the robotics, autonomous robotics, are the same attackers, mostly same mitigations, same risk, same probability that they can harm people. So what are the autonomous mobile robots? Basically, autonomous mobile robot, it's a robot that can understand and move through an unknown environment independently. They are an evolution from autonomous guided vehicle that were moving through a predefined path. Unlike them, think about autonomous mobile robot like a self-driving car for specific use cases. We can see them in agriculture, we can see them in manufacturing, we can see them in healthcare, in any fab. And those robots are not so cute. They are not just a small Roomba that you have at home. They are big robots capable of moving weights between 100 and 1.2 tons, even 2 tons. Think about a small car without driver that move autonomous side by side with human being. Those are already in use. This is the reality. It's not a science fiction. And if you're looking on the last year report of the most critical cybersecurity trends, we can see that the cyber physical systems take a good place in the middle, the 10th place, just because those systems became autonomous. And they recommend to increase increase the security measures through encryption, authentication, and monitoring in order to prevent those systems from damaging environment and human being. If we're talking about the robotics, I have to mention Isaac Asimov and the 3 laws of robotics, the main 3 laws of robotics, because there are few others. And remember, the first law was a robot may not injure a human being. The second, a robot must obey the orders given by a human being. And the third, the robot must protect its own existence. When we're looking on the industrial robots, I think 3 fundamental laws apply. The systems must read to the physical world correctly and write, for example, perform some specific action, and never harm human beings, like Asimov specified. Now, those systems have a huge amount of safety features inside, embedded, and I want to give a short overview of maybe some of you know of a computer worm called StackNet. This is not a new worm. It was released in the wild in 2010. Many believe that it is developed, or it was developed by US and Israeli governments. They think that it was developed even 5 years ago. The thing is that this is a worm that actually infected industrial control systems. This worm basically attacked the SCADA systems, abused the safety system of uranium enrichment centrifuge, and caused them to spin way too much behind their operational parameters, and causing those systems to a permanent denial of service or permanent damage. But as simple as that, they could cause those systems to explode or to cause the environmental damage. I'm just showcasing here this example because safety systems are systems, and they are meant to break. This virus was raised in the wild. Many actors, many attackers have possessed its code, and they reverse it, and they reuse it, and they keep using it in different flavors. And those systems are meant to be break. If we're looking on the AMR ecosystem, I'll bring here some examples. For example, you can see that this is a nice hospital robot. It was breaked, it was hacked. The remote attackers will be able to hijack it and control it and crash it into the people and personnel in the hospital. They cause disruption in the hospital and much more. This, for example, it's a relatively small robot. Other security research company, Thread Micro, also research this domain, and they find out that the attacker can basically alter the control parameters and tamper with the calibration of the robots and alter the robot states. Eventually, this can cause to crippling of the production, damaging property and human beings. So similar autonomous systems exposed to attackers. Another research from a university also showed that the attackers can control those systems and move them as they will and cause damage to the environment. The attackers can also basically hijack the robot. So during the COVID, we find Alkerblitz is basically a ransomware for autonomous robots. We have a vendor called Universal Robotics. They were impacted. Those robots were used for health, for sterilization and stuff like that in the health, disinfection in the health industry. And during the COVID and crisis time, they were hijacked. And besides that, the attackers can also leak confidential information. Those systems are collecting a huge amount of data, and they can be used for espionage. The Chinese self-driving car were found out that they are collecting the data and share it with the mainland. And that's why basically they've been banned from the US. In the agriculture, those also were attacked. So everywhere we see those systems, we see different types of attacks, and they can cause basically a global supply chain, a food global supply chain attack. Why? So let's understand that those systems, as I explained before, they are very, very complex. They're not just the robot itself. Usually you can see we have a robot that can move from a point to another. It has a lot of sensing capabilities, motion control and everything. Usually those robots have on top of them some lifts or some modules like robotic arms, and they are supposed to be isolated, but they are usually controlled by a server. When I say control, the server delegates them tasks, move from here to there, do this operation and such. Those servers eventually they are also connected to additional systems, like fleet management system, like data analytics, like fab manufacturing management, and any other system. So at the end of the day, those robots are connected to the internet, to the enterprise, and the attacker can abuse them. Besides that, need to take in consideration that every single component in the system, it's a very, very complex, composed of different modules and building blocks. They use communication to communicate between each other, usually Wi-Fi or 5G, and they also come with an additional set of tools, SDKs, calibration tools, many, many other tools. All those are basically an attack surface for attackers. I put here just an example of what is basically inside a simple robot. And you can see that there is a stack of application that is built on top of different frameworks. Some are open source, some are proprietary. Besides that, we have a huge amount of compute, more than one system, more than one compute. They have a huge amount of sensors, and they use a lot of communication capabilities. So the complex the system is, the breakable and most easily attackable it is. The goals of AMR attackers are basically to tamper with the control parameters and to tamper with the calibration parameters and production logic, and basically they want to fake the robot signal or user-perceived robot state, or even to tamper with the robot state. And the goals, basically, they seek to cause denial of service in the manufacturing, because at the end of the day, that will cause an economic threat that can be monetized, and they will seek to halt the production. In some other cases, we see that they try to alter the production line, to delay, to change the outcome. So, for example, if a robot is responsible of doing something, they want to tamper with the output. Manufactured parts can be used in some other system and then have other problems. We saw the ransomware schemes, device hijacking, and of course, physical damage. The most critical part is physical damage. Besides that, we see additional attacks that will basically try to do espionage, to leak sensitive data, and additional things. In order to mitigate those attacks, we need to think about risk assessment, to analyze the systems, to use cybersecurity standards and frameworks, and most important, to collaborate with different vendors. Think that the robots are manufactured by one vendor, integrated by another, and operated by another. So collaboration and synergy between them, it's crucial for protecting those systems. Now I'm going to talk a little bit about different attacks per layer from a point of attacker, and how to mitigate those from a point of defender. As I say, I'm focused on defensive approaches. So if an attacker will try to abuse the firmware and the software, he will usually try to roll back those software and firmware to a deprecated vulnerable version. They will try to load even a software or firmware that is not signed maliciously, or they will try to abuse the OTP that controls some security capabilities. They will try to abuse the over-the-air software update mechanism. At the end, they will try to seek to change basically the commands and the parameters that the autonomous system it's operating under. Of course, they will try to abuse also the web management interface. In order to mitigate those attacks, we can utilize anti-rollback. Anti-rollback mechanism will deny rolling back to previous vulnerable versions. Of course, we need to secure the software and firmware updates. We can do that with signing to secure boot. We need to emphasize OTP wear-out protection. In some cases, you should consider encrypting your software and firmware. Again, that depends. And definitely, we need to limit the management interface and use only secure access. Another layer of attacks is networking. As I said, those systems are interconnected. They usually use Wi-Fi, LAN, GPS, Bluetooth, RF, and 4 and 5G. Any attack on those are applicable to those systems. Usually, this is due to insecure communication. And in many cases, we see that they are using an unstable or undefined or poorly defined network. But in most of the cases, it is using the denialist topology. We don't see component isolation, meaning that the robots are accessible from the wide web. Why? And I also detect hidden connections. So I found vendor that is transmitting back to its own servers, telemetry and logs and such, but hidden. So we need to mitigate those by, of course, securing the connections. We need to secure the traffic, encryption. We need to use secure network protocols. We need to define a topology based on a allow list. Network segregation and component isolation. So all the robots in a specific environment can be isolated from the external world. We can do that through firewalls. We can do that through firewalls that can be on the robot itself, on the network level, and also utilizing intrusion detection system. On top of that, we need to constantly monitor and audit for any abnormalities, because those systems will be attacked, and without doing that, we will not be aware of that. Hardware and system. So people forget that those robots are operating remotely somewhere. When I say a warehouse, it can be twice or 3 times or 10 times or 100 times bigger than this facility. Usually nobody is near the robot, so nobody can protect the robot physical security. What I list here is just a sample for simple hardware adversary, but think about that an adversary can abuse the robot, can access its own compute, the buses, can access the memory, the privileged memory, can steal the memory, the disk, and basically can gain additional insights, can abuse the unprotected login, physical login, local access login, through the terminal, through the USB, and again, any interface, it is exposed and it is an attack vector. The mitigation should be, again, those are only partial mitigation. Securing those internal buses that are sensitive and access sensitive information, like putting in place VTD and VTX technology, we can protect for PCI Express, but this is just an example. Disk encryption. If I'm an attacker, I'm gonna steal the disk, I can throw it again to the garbage, because if it is encrypted, I can't abuse it anyway. Any unused interface should be disabled, physically and in software. And then we need to secure the interfaces that we are using. Besides that, we need to deny any local access and allow only remote SSH. And I would recommend only use certificate, because user password can be brute force eventually. At software and firmware layers. So again, there are supply chain attacks. There are utilizing and abusing third-party components that are insecure and vulnerable. And I see time after time using deprecated and old frameworks. Like in the robots, in the autonomous robots, we have ROS 1. Now there is ROS 2. Now there is ROS 2 improved version. We should use those. From software security development, again, we need to do secure development life cycle. We need to do this process, doing security over all the development layers, from architecture development and validation. We need to utilize secure best code practices. We need to manage the SBOM. So internally, we have a huge amount of artifacts, of executables. We need to manage what we put, from where and why. Utilizing vulnerability scanners, static code analysis, binary scanners, they are also going to reduce the vulnerabilities, will expose the vulnerabilities in the systems. Of course, we need to scan the pipeline and run constantly vulnerability tests. OS level, so those robots usually have OS, more than one. Definitely, it is an attack surface, it can be abused. Vulnerabilities at the OS or the third-party packages that are deployed with the OS, and any executable in the system, it's a good target. In order to mitigate that, we need to do OS hardening. It's rarely done on those systems. Of course, we can use secure flavor of the OS. We need to use and run anti-malware and antivirus on those systems. We should do execute hardening. Basically, we can compile the binaries, our binaries that we developed with the relevant security flags in order to harden them. Of course, those systems need to be patched up to date, both OS and the additional third parties components in use. Usually, I'm seeing in those systems that they come with huge amount of unneeded components. They need to be reduced in order to reduce the attack surface. And in some cases, need to take in consideration that embedded systems are less secure, and we need to improve them by moving to, if possible, to non-monolithic OSs, where we have at least different separation between the kernel and the user space. The sensors. The problem with the sensor is that everybody thinks that they are foolproof, and the problem is that they aren't. They are always easy to abuse. I'm not saying that they are easy hackable, but they are easy to abuse. Sensors like camera, LIDAR, radars, ultrasonic, thermal, safety, you name it, GPS, they can all be spoofed, they can be abused. For example, with infrared, I can abuse the camera. LIDAR and GPS can be spoofed. Attackers can use the laser and reflectors and any other tools just to interfere with the sensors data, so it can blind the system. On top of that, we see that attackers can abuse those sensors by utilizing and injecting or installing malicious software or firmware or even calibration data. For example, if I have a camera and it has a calibration parameters, if I'm going to put wrong calibration parameters, the robot will not stop at the right place. The mitigation are simple. I would say never rely only on one sensor. This is a defense in depth approach. You will see about that in a minute. More than one. In the safety systems, we need to use at least two. Of course, many sensors have safety versions. If you are not required by the standard, probably you're not going to use them, but use the safety versions. They are more secure and they are safety. My most important mitigation is basically to don't assume anything, test for the all corner cases, and assure that the systems will always fail safe and secure. So even if a sensor is blinded by something, by environment, unintentionally or intentionally, the autonomous system should stop safe and secure, or should perform safe and secure. If possible, I recommend to sign all the calibration data for those sensors, because in that way, nobody can tamper with that. One last, and again, due to time, there are additional attacks vectors, but the last one I'm going to touch is the identity and access management. So I've seen vendors with no authentication. They are open by default, or even weak authentication. They still have some user password that can be brute force. The worst I've seen that they embed credentials, meaning that the credentials are embedded on the flash. So if I, an attacker, will break the system, I can break it once and reuse it everywhere. Bore attack. So the mitigation, of course, are also straightforward: strong authentication, password policy, password rotation. Not one password for all systems. That's a big problem. I see many robots using admin or root, I'm running as root because it's easy, because it's simple. In some cases, there is only one account, admin account. Try to move to more than one account and run the systems with the least privilege needed. And utilize mechanism into the OS to avoid brute force. So there are mechanisms that will delay the brute force attacks. To summarize, basically, we see that those system architecture is multi-layered and multi-dimensional. So they are complex. And usually the attackers will find the weakest link in order to break it. So in order to protect it, the only good way to do it is to follow the security principle of defense in depth. So the idea is to put multiple layers. So even if an attacker will break one layer, he will still have multiple layers of protection. So those systems eventually will be good enough, secure enough. Never rely on one layer of protection. Think about the metaphor of onion, multi-layers, and lobster. Hard from outside and very tasty from inside. Easy to break. So I talked a little bit about security. I want just to touch the safety aspects of those systems. So first of all, the safety is protecting the environment from a given system, okay? Safety focus is to protect the environment, where the security is to protect the system from the environment, okay? Many people that are not from security domains, they are mismatching those terms. You need to understand that there is no safety without having security. Of course, there is also, we rely on quality and on additional things, but safety without security, it doesn't exist. Many people focusing on putting safety mechanism on the systems, and they say we are safety, and they're not investing at all in security. Well, this is a big misconception. So the goal is basically to utilize the unified security and safety risk framework to define what are the safety goals, to see that they are achievable and that the safety mechanisms are secure. Those systems are challenging and need to keep in mind that security eventually will improve the safety, will protect the safety mechanism. So without having security in place, the safety won't stand. The sources of safety or the hazard basically vary from the human error to control errors to unauthorized access, malicious access, okay? But we can also see additional issues like mechanical failures and time pressures and environmental issues. But think about that through unauthorized malicious access, basically we can mimic and fake all the other sources of safety hazards. And we can create them synthetically. We don't need actually today to happen, we can mimic them. So how security is basically protecting safety? Through network security, we can achieve network isolation. So safety systems should be isolated. We need to emphasize authentication and authorization in order to access those safety components. Those safety systems are consuming data in rest or in traffic. We need to think about protecting it by need. We do have vendors and they provide secure software update and over the air with anti-rollback. So without proper patching, those safety systems over time are vulnerable. It's important, and I repeat that again and again, to sign related configuration and calibration data for those safety systems, because we have a safety system protected, and through tampering those calibration and configuration files, we can basically make them unsafety. On top of that, we need to constantly audit and monitoring those systems and detect unexpected behavior or errors. So I talk about safety isolation, and in safety there is also a principle of redundancy duplication. So have more than one safety mechanism in order to prevent that if somebody is attacking one, the second can act instead of it. And I would say, and most of the safety people will contract me, but I will say any safety complementary control, it's a good defensive mechanism for the safety certified systems. The safety guys will come and say the safety system is certified, it's secure, nobody can hack it. Well, this is wrong. It's proved time after time. So usually to have a safety complementary control, it's better because you can double check what happened with the safety system that you rely on it. So we discussed now about a lot of security topics, and this is like a short list, a partial list, and this slide basically shows that every single entity that is responsible of those robots, from manufacturer, integrator, and operator, are participating and need to do those security activities. Design for security, do threat model, do risk assessment, do secure code review, patching, management. But you can see that no one of those activities, it's basically, or most of them, they have shared responsibility between different owners. So it's important to understand that I, as a manufacturer, can secure a system, but then the integrator can provide it unsecure or without security configuration, or the operator will use it insecurely. So safety and security of the system, it's a shared responsibility between the manufacturing, the additional vendors, of course, the robot integrators, and the operators. So I started with the Industrial Revolution and the rise of the generative AI and Industry 4.5 and 5.0, and I want to talk a little bit about AI. Okay? At least I have 5 more minutes to touch a little bit the AI aspects of this evolution. So in the past, we used regular software, and today basically we have LLMs and we have generative AI, and we'll see that it is starting to basically be integral part of those autonomous systems. And in the future, we're going to be seeing autonomous AI agents or autonomous systems that have AI evolving and learning and constantly adapting. Those AI, generative AIs, and in general AI, they are used for perception, for sensing, for decision making, for predictive modeling, for map generation, for natural language interfaces. So it is basically a good utilization of generative AI in autonomous systems and autonomous vehicles. And if you think about that, we started from manual labor to semi-automated labor to automated labor. Now we're talking about semi-autonomous and autonomous, and the future will be symbiotic autonomy, meaning that in the future, maybe in our lifetime, maybe sooner, in the next years, we'll see robots that cooperate side by side with human beings, that they are constantly learning and evolving. I know maybe it sounds a little bit frightening, but it is the direction that we're moving forward. And it's not science fiction, it is here to come. So that's why basically we need to think about that before we're gonna give them that autonomy and work with them, we need to assure their safety and security against, of course, hacker and themselves. That's very, very important, because otherwise we may have a reality of Skynet. It may be real. Okay, to summarize. It's important to do secure by design. I think this is basic. This is an intro lecture, so very important approach. Cybersecurity, I show here today that it is a still immature field. This domain evolving much faster than the security mitigations for it. Of course, we need to implement security from the design all the way through the manufacturing, through the implementation, through the integration and the operators. We need to take in consideration the entire ecosystems and entire building blocks. Software in use, firmware in use, sensors in use, hardware, end-to-end, everything together. We constantly should identify new threats and test for existing vulnerabilities and ensure that we have controls that are sufficient and effective. It's not just one time and that's it. The domain is always evolving, and that's also applicable for most of the domains in security. So we need to always seek new attack vectors, new attacks, and add and move through more advanced technologies. So to summarize today, we talk about autonomous systems. They are complex, so we need to design for both security and safety. Defense in depth is the security principles you need to follow. Remember, it's a shared responsibility between all the parties, and there is no future for autonomous systems without safety and security. Do call me if you want to collaborate and cooperate, or you have any similar problems, and we can collaborate together. So thank you, BSides, for inviting me here for first BSides in Strasbourg, sorry. And it is my honor to be here, and thank you very much. If you want, I can be here for questions, because I'm not sure there is no microphone, so I can be here and answer questions. I will come down.